Ok, buonasera a tutti e benvenuti a questo webinar dal titolo HEC RAS 6.1 del Breeze Flow e 2D Sediment Transport. Stasera c'è una novità che non avevamo programmato, ci sarà anche con noi Alex Sanchez. Hi Alex, insieme a Stanford, che naturalmente aveva già dato la sua disponibilità. Parto velocemente con una presentazione in italiano, poi passerò la parola a Stanford che ci illustrerà la presentazione. Alex sarà infine disponibile insieme a Stanford per le domande. Allora, questo webinar è disponibile sul canale YouTube Modellazione Idrauliche GIS. Vi invito anche a iscrivervi al canale YouTube di Stanford, che vedete qui in questa immagine. Stanford Gibson è specialista degli studi di trasporto solido presso la HEC, dove lavora da circa 20 anni. È responsabile dell'implementazione degli studi di trasporto solido in HEC RAS sia 1D che 2D. Stanford applica regolarmente anche modelli per supportare il ripristino dell'ecosistema, la riduzione dei danni da inondazione, progetti di navigazione e ha insegnato idraulica e trasporto solido in più di 10 paesi. Vi invito velocemente a iscrivervi anche al mio canale Facebook HEC RAS Italia, il canale Telegram Modellazione Idraulica e GIS. Inoltre, per chi già la conosce, naturalmente lo ha già fatto, vi invito a iscrivervi all'interno della newsletter. E inoltre, la prossima settimana, il 17 dicembre, terrò un webinar dal titolo A danno dall'alluvione del fiume Panaro, nel quale presenterò il modello idraulico calibrato all'evento di lettura dell'argine in destra idraulica in località Gaggio. Vi invito anche a prendere visione del corso GIS applicata all'idrologia e all'idraulica, che ho già completato come numero di partecipanti. Per questo terrò una nuova sessione nel febbraio del 2022. Per ulteriori informazioni potete inviare un'email all'indirizzo indicato in questa immagine. Inoltre, vi segnalo i miei libri HEC RAS Moto Permanente e HEC RAS Moto Vario che sono disponibili su Amazon. Stanford, let's go.
All right.
Go. Ok.
All right, well, welcome. My name's Stanford Gibson. I'm the Sediment Transport Specialist at HEC, and we're also joined today by Alex Sanchez. Alex Sanchez is kind of the numerical specialist at HEC, but he also wrote the code for almost everything that we're going to show you today. He developed the 2D debris flow and the 2D sediment transport. So I'm going to present them, but it's a lot out of Alex's work. And so Alex is here, and he's going to be able to answer questions in the chat. Go ahead and put any questions you have in the chat. He can answer them. Alex is also a Spanish speaker, so if you'd rather ask your question in Spanish, he's more than competent to do that as well. All right, so I'm going to cover two topics today. These are both brand new in version 6.0, and they've been improved in 6.1. They'll be further improved in 6.2. We're going to talk about the new mud and debris flows, the non-Newtonian mechanics in HEC RAS, and then we're going to talk about the 2D sediment transport in RAS. Okay, so in 2018, January 2018, there was an intense rainfall event in the mountains north of upstream of Santa Barbara. The problem with this rainfall event, it would have been fine. It would have been a moderate flood, but the mountains upstream of Santa Barbara were on fire, and 90% of the watershed had been burned. So this intense rainfall event that would have caused a moderate flood, instead, it mobilized a lot of material, and it caused a debris flow, a mud and debris flow. 23 people were killed. It caused over $200 million of damage in USD. Just over 1 year later, in Brazil, there was a debris flow in Brazil, a Mindtailing dam failed, and this Mindtailing dam failed and killed 270 people and released 12 million cubic meters of sediment. The legal damages from this event are reaching about $7 billion. This is the fourth Mindtailing dam failure in Minas Gerais in the last 10 years, and there have been a number of these events around the world. And so both of these issues, post-wildfire sediment transport, post-wildfire debris flow, and Mindtailing dam failures, these issues are just going to get worse. Climate change is causing more wildfires, and our Mindtailing debris dams, they're just getting older and more full. And so we want to be able to simulate these with a flood risk management tool, and a lot of people use RAS as their primary flood risk management tool. The problem is that these are not clear water flows. These are what we call mud and debris flows, and they require non-Newtonian mechanics. And so if you were to, the idea behind the problem with non-Newtonian mechanics is that to say mud and debris flow, it's not just one thing. The idea is that as you add solids to a flow, the physics of the fluid changes. And so as the physics of the fluid changes, you get more losses due to the solid interactions. And so in general, the more solids you add, the more internal losses you have in the fluid. But also, the coarser your sediment gets, the more internal losses you have in the fluid. And kind of a standard approach with HEC RAS, just clear water flow, it wouldn't get even close to the result of either of these events. And so what you see over here on the left, this is the basic concept of clear water flow. We have our fluid that travels through our domain, and most of our losses are at the boundary. We have these friction losses. But in the non-Newtonian flows, you still have those boundary losses, but then you also have losses from viscosity of the material. You have losses from particle collision, and at some point you have enough solids that you have solid on solid friction, and it starts to become more of a geotechnical material. The problem is that all of these things can happen during an event. And so having a tool that can simulate each of these or all of these is going to be really helpful for simulating these events. So how we integrate them into HEC RAS? This is the one-dimensional form of the shallow water flow equations that we use in HEC RAS. We'll generally do this in 2D. You can do mud and debris flow in 1D or 2D, but it's just going to be a lot more stable in 2D. Almost everyone's doing it in 2D, but it's easier to understand in 1D. And the idea here is that we're actually going to modify the momentum equation in order to incorporate these mud and debris losses. And in the momentum equation, we have a friction slope, and that's how we integrate the Manning's loss, the boundary friction. Well, we're just going to add another slope loss term that we're going to call the viscous and internal loss term, and we're going to add that based on these other processes. Well, how are we going to get that? Well, the convenient thing about a friction slope is that if we can develop a shear stress, we can develop the friction slope. And so the idea is that for these internal losses, if we can cast these internal losses in terms of a shear stress, we can compute an internal loss slope that can go into the momentum equation. And so how are we going to quantify these internal losses with some sort of shear stress? Well, that's where we bring in the science of rheology. Rheology is it's the science of how materials deform. When you apply a stress to a material, it deforms or it strains. And so there are a number of different models of how different materials strain. And so, for example, a clear water fluid it's just a Newtonian flow. And so you have a linear stress-strain relationship that has an intercept of 0. But kind of the simplest non-Newtonian model is you still have a linear stress-strain relationship, but now the slope is the viscosity of the material, and the viscosity is higher because you have solids in it. And then you also have a yield strength. And a yield strength means that the fluid can now come to rest because there's a strength in the material that is non-zero. Essentially, water will just keep moving until it reaches a depression. A debris flow will move until the strength of the material exceeds the driving force. And so a debris flow can come to rest. And then there are more complicated rheological models, nonlinear rheological models that get into shear thickening and shear thinning. I have a couple of videos that go into this in more depth, but that's all the theory we're gonna handle for now. The idea is that for each of these different processes, we can use a different rheological model to look at how the material strains under stress. And so we've incorporated these rheological models into RAS and then add that to the momentum term. And so let me just show you how it's working. I'll show you one kind of lab scale validation and one kind of mesoscale validation, and then kind of show you the models of the two scenarios I talked about. So this is a flume that was developed by Parsons et al. About 20 years ago. It was just a pipe. It was a half pipe, and they put material, lots of different kinds of very high concentration material. We're talking about 80% concentration by volume, and some of these things are very fine. Some of them are clays, others are very coarse, lots of clastic material. And so I modeled this in RAS. I started with a cross section to get my half pipe, and then I converted it to a terrain in RAS. And this terrain has 13,000 cells and 1 millimeter resolution. I think there's a chance that I might have the record for the finest resolution mesh in RAS. But we developed this pipe in RAS, and then we modeled just clear water. We put clear water through this half pipe, and then we added the non-Newtonian parameters of the actual experiment. And you can see this is what would happen. The top is what would happen in clear water. I've zeroed in on it a little bit here. The top is what would happen in clear water, and the bottom is what happens when you add the measured non-Newtonian parameters. And what you can see, I actually have modeled it to the point where they took a picture of it, and we're not only modeling the extent of this flow, but also kind of the shape and the depth of it as well. And so that's kind of anecdotal. How does it work in general? Well, they did a bunch of experiments with a bunch of different materials. And so and they observed the velocity of the front of the debris flow. And so this is the observed velocity on the x-axis. And here is the HEC RAS computed velocity. And what we have up here, the blue ones, are the clear water flow, if you were just to use RAS in the version 5. And what you have down here are the mud and debris flow, the non-Newtonian solutions. And you can see that the non-Newtonian solutions then collapse around unity and provide a much better result. If you look at two of these in particular, and when you look at how it's computing velocity across the cross-section, because of the new turbulent stuff that Alex added, you can see that they went and actually measured the lateral velocity as well. And so we looked at the measured and computed lateral velocity from RAS, and RAS is not only getting the front of the debris flow correct, but it's actually doing very well with the lateral distribution of the velocity. So we have a paper on this, and we looked at lots of different non-Newtonian parameters. One of the cool things about this paper is I developed a multimedia methods and materials. So basically, we have on YouTube, we have these videos where you can actually go through and create this model from scratch and then run it in RAS and have the kind of same experience of developing this model that we had. And you don't have to read it, it's in YouTube. And so kind of the gold standard for validation of mud and debris flows are these large-scale flume models done in the Pacific Northwest by Richard Iverson, who's the mud and debris flow specialist in the USGS. And they have these mesoscale experiments where they release large debris flows down this massive slope. And they've just done this for years. They have a great database of all of these different experiments. And so this is really the gold standard for debris flow validation. And so we did that. I again built the terrain in 1D because it's a pretty one-dimensional terrain. And then we converted it to the 2D terrain. And Alex simulated these in RAS. And so what you can see here is they have these observation points where they look at the depth time series as the debris flow comes through. And so the black curve is the computed time series, and the blue curve is what they measured. And you can see we're getting the front and kind of the shape as well. And then this is the final plume when the debris flow comes to rest downstream. We've got a picture of it here and the actual simulation. And this is the difference between, this is one of the differences between debris flow and clear water flow. Clear water flow would just continue to run out until it reached a high ground. The debris flow will come to rest because it has a internal strength. Okay, so how did we do in the field? Well, this is the Santa Barbara model. And what you can see, this is the model from the Santa Barbara debris flows. And what you can see is, here is the blue is the boundary of the observed mud plane of this event. And what we've got here, this is what RAS clear water flow does. If you just put this event in with clear water flow and RAS, we like badly underpredict the actual extent of this event. But if you add the non-Newtonian parameters, this is the result. And now you can see that we're actually doing much better simulating this event. And actually, this is a calibrated model, but we did this model with just best estimate parameters. We said, you know, if you went to Julian's, someone messaged me if
you're back.
Can people hear? I'm back. Okay.
Yeah.
So the gist of this slide was that you know, these parameters can be difficult to come up with. So we actually just used parameters from the books, regression equations and Julian's textbook. And this is the result you get just using the parameters from the book. That's actually, this is a pretty strong result because it's so difficult to estimate these parameters, but we put the default parameters in RAS and got pretty good results. Then you have the Brumahilo Mindtailing failure. And this is one of the things that made this event so remarkable is that they caught it on video. And so this is, most of you have probably seen this this on YouTube. It's, you know, one of the biggest events of you know, of the last 10 years of geophysical flows. And this obviously is not a Newtonian fluid, right? This is not water. It's not traveling like water. Is my volume okay? All right. They had these 3 locations where they had measured arrival times. And so we not only reproduced the mud plane, but we also were within 2% of the arrival times when we simulated this event. One other thing that's really fun, Alex has been collaborating with an Icelandic engineer, Horn, whose Icelandic last name that I won't attempt, but she's been doing some work in emergency management with the lava flow that's happening in Iceland. And what she did is she tried to use the non-Newtonian parameters to iteratively solve the lava flow, and she actually did quite well. And so what Alex did is he went in and put in a very basic heat budget so that 6.2 actually will have lava flow in it. And here is the lava flow simulation that he developed, because the colors are temperature. Yeah, red is the hottest material and how it's cooling as it extends. This is going to be in 6.2, and it's really fun. Okay, and so that's the non-Newtonian stuff. That was all funded by the post-wildfire flood and risk management program in the Corps of Engineers. And now we'll transition to the second topic, which is 2D sediment in HEC RAS. You see, everything we've done so far, even though we've added solids to our fluid, it's all been fixed bed. We haven't actually done any deposition or erosion yet. And so for really high concentration fixed bed material, you want to use these non-Newtonian solutions. But we also added 2D mobile bed. And this is something Alex has been working on for 5 years. The big release in 6.0 is the culmination of 5 years of work. And there are just a lot of advanced features. It's not like we kind of released a skeleton version and are going to improve it over time. This is a model. It has all the things that you'll want: mixed cohesive and non-cohesive, hiding exposure, bed slope effects, avalanching, hindered settling, consolidation, flocculation. It has all the things that you would want to do a robust 2D sediment model. It solves the non-equilibrium equations, and but the thing that's really remarkable about this model is that it's a subgrid model. So those of you who are familiar with RAS 2D hydraulics, the thing that's special about RAS 2D hydraulics is that the grid cell is not just a grid cell by itself. Each grid cell has what we call subgrid hydraulics. And so we know things about each grid cell on the subgrid scale. We take the grid cell and we develop a volume elevation curve of the grid cell itself, and each grid cell has cross sections on every face. And so we actually know how water passes into and out of the grid cell based on the cross section of this face. You could kind of think of it as every grid cell has a one-dimensional model on every face. And so this is one of the things that's real, and this is actually based on an Italian model. The scientists that first used subgrid were from Italy, and we followed a lot of the work they did. And the power of this is you can use a much bigger cell because each cell has more information built into it. And that's great, but that was a challenge for Alex because now we had to add sediment transport to this subgrid model. And so the sediment transport model actually does compute sediment transport on this subgrid scale. And we have talks about that. Alex and I just taught a class on this, and we recorded it. And so as I edit those files, they will end up on YouTube. But for now, let's just kind of show you what it can do. And so I'll just show you 2 laboratory scale models and 2 prototype scale. And so the first one, Alex did this one, is the Weiss expansion contraction flume. And so this was a flume in 2002, I think in Germany, where basically you have flow that comes into a rectangular channel, and then it contracts into a narrow channel, and then it expands. And so when we're teaching this, we like to develop a hypothesis. What's going to happen? Well, as the flow contracts, you're going to scour, and then as it expands, you're kind of going to give that sediment back and deposit. And so this is what the concentration and capacity maps look like in RAS. You can see that as you erode, you increase the concentration, and this shows the capacity as well. And so then this is what the bed change looks like. The bed change, in general, when we map bed change in RAS, Alex and I like to use this map where blue is positive or deposition and red is erosion. And so if you look at a cross section, a longitudinal cross section down the center, this is what the hydraulics look like. And so the hydraulics dip a little bit as it contracts, and actually we're not totally nailing the hydraulics on the expansion. There's a little bit of a divergence there. And then if you look at the bed change, we're actually getting the bed change really well through the contraction. We're getting the extent of the deposition on the downstream end. It's because of the hydraulics, it ends up depositing a little early, but the magnitude is pretty good. Another model that we've been working on recently, and this is actually we're still working on this, but it was cool enough that I wanted to show it, is a floodplain deposition flume. This is 𝗡𝗘𝗪𝗦𝗟𝗧𝗧𝗘𝗥 and his crew out of a lab in Germany, and they were looking at floodplain deposition in the flume. They kind of built this half channel with a floodplain, and they modeled it both with plastic and with sand. One of the cool things about 2D sediment is that you can put in variable density. And so we put in the density of the plastic in here and modeled it both with plastic and sand. they had some data as far as, what was the deposition on the overbank and what was the gradation of the deposition on the overbank. And so we built this terrain in RAS. It's just a standard RAS terrain, and then you can see that this is the plastic particle analysis, and the magnitude of the deposition scales to the deposition we see in the channel. I have a video of a different one. This is the stand analysis, and basically, the flow is going from left to right, and you can see that we're getting more deposition in the channel. This is the value here is bed change, and we're looking at it in time at this profile. And so you can see that we're getting more deposition in the channel, but then we get this tapering deposition in the overbank. All right, so Alex probably done a dozen to 18 of these validation and verification models. But then we have started to do like larger prototype scale studies to demonstrate this. And so this is the Chippewa dredge study. The Chippewa, we're in the central northern United States in a place called Wisconsin, and the Mississippi River flows through here. This is the Mississippi River, and then a smaller river called the Chippewa River flows into the Mississippi River. And the Chippewa River brings in a lot of sediment, and the delta of the Chippewa extends into the Mississippi River and blocks navigation. And so the Army Corps of Engineers is in charge of removing all this sediment, and it's incredibly expensive. And so we built a 2D model to look at different management alternatives. The one thing that I'll say, here's the mesh and the bed material that goes underneath it. You can define a bed material map and then use the bed material map to associate gradations. You can also have stratigraphy in the 2D model. But one of the things that I want to point out is we probably spent more time on this mesh than on the sediment model. One of the things that you'll see in 2D sediment is very sensitive to hydraulics. You have to get the hydraulics right before the sediment will be good. And so we put a lot of effort in, we put more effort into a good mesh and a good hydraulic model if we're going to do sediment, because the sediment will kind of reveal issues with your hydraulic model. And so this model was calibrated 3 different ways for hydraulics. This is just a profile line down the center of the Chippewa and into the Mississippi. And you can see that a lot of times the best way to calibrate a 2-dimensional model is to kind of one-dimensionalize the result. And so here we have the profile line from the 2D model and observed water surfaces for a specific event. It was also calibrated in time. And once we had the calibrated hydraulic model, then we could add sediment. And so this is we actually simulated a event that was captured in Google Earth. So you could see this is the delta that impinges into the Mississippi, and then this is the simulation of that result. And then they had dredge polygons, so they had a sense of how much sediment had been removed there. And so the model went in and we compared the dredge sediment to the sediment deposited at that delta. And so that's what you're looking at here. You're looking at the deposition in feet, because we did this in the United States and we still use old units. All right, and then finally, Alex did this one. This is a validation of the upper Mississippi. This is about a 9-kilometer model, and it was simulated the time period between 2014 and 2016. And so this is a pretty detailed mesh, because we needed to go in and we used break lines and non-erodible surfaces to define all of these structures that are in the Mississippi River. These are navigation structures in the Mississippi River. And then we calibrated to a high flow and a low flow. Again, we got to make sure that the hydraulics is right if you've got any chance of the sediment transport to work. And then we simulated an event. Alex did the sediment transport, and over on the right is the measured, and on the left is the computed. And we're eroding in the right places at the right magnitude, and so the model is working at scale. This is the biggest river in the United States, top 15 river in the world, and it's the model is performing at scale. Okay, so just to wrap things up, we've talked about non-Newtonian fixed bed, and we've talked about mobile bed sediment, but what if you want to do both? What if you actually want to have non-Newtonian parameters and also move the bed? Well, so far you can't do that. In 6.2, you can't do that, but that's one of the things Alex has been working on is the he's connected the non-Newtonian simulation to the mobile bed sediment. And so that's something that that's going to be available soon. And this is a dam breach. Laboratory model where you have very high concentrations, but it's also mobile bed. And so a mobile bed non-Newtonian solution is the best way to approach this. And so basically you've got a dam that's going to fail and put a bunch of sediment into the flume, but the flume also has an expansion. And so it'll capture both of these. And so this is what the simulation looks like. The sediment rushes into the expansion and then expands. You've got these recirculating zones. And so, and this is what it looks like afterwards. And so what Alex did is he went in and he put these observation lines in and measured the water levels over time. And so here you can see the measured and computed water levels downstream at the expansion, and then the final bed change. And so you've got variable lateral bed change because of the non-Newtonian and movable bed, and the model's doing a pretty good job with the non-Newtonian mobile bed solution. All right, so then I'll just finally say that all of our users' guidance is moving online. We've got the mud and debris flow user material. We've also got the 2D sediment transport user material. If you are still using the PDFs are going to go away. We're going to go to this, and we're kind of moving away from sediment manuals to what we're calling like an online user help experience. A lot of the videos that are on my website we've just embedded into the user's manual. So if there's a video there, you can search on the user's manual, it'll show up right there. We're adding a bunch, we've actually started a RAS channel, and with 6.2, we're gonna release the RAS channel that has the whole 2D hydraulics class on it. And then we'll start interspersing those in the user's manual, because we just know that most people, most people live in Antonio's world. Most people want to go to YouTube to learn this and don't want to read it from a PDF. So that's where all of our user help is going. And with that, I have two videos on the non-Newtonian that people could use. But Antonio, I'll turn it over to you.
Stanford. It's okay. Okay. Finish. And okay. Thank you, Stanford, for this great presentation. Now for all questions in chat, okay? I show this first for you, Stanford.
So the question is, did you use brake lines for the mesh modification in the case of the Chippewa River? It was impressive and specific. Were the modifications based on bathymetric measurements? Yes, we used a lot of brake lines. Let me go back to that slide for that mesh. Let me actually stop on the Mississippi along the way. One of the things that I think distinguishes advanced 2D RAS users is just how you use brake lines and refinement regions. We use the brake lines. Here we're using brake lines to define these structures, and then when you move to sediment, it's actually more important because these structures are non-erodible, and so we actually have to identify these as non-erodible materials. Otherwise, they'll erode in the first time step. But then in the Chippewa, we used a lot of brake lines, but the other thing we did is we used refinement regions. If you've got a channel like this is a quasi 1D channel here because the channel is only 1 cell wide, and you can't do that with a brake line, because if you go in and put a brake line, it will at least create 1 cell on both sides. And so if you want a quasi 1D channel that has 1 cell wide, the way that I do that is with a refinement region. I draw a very detailed refinement region along high ground, and then I enforce a 1 cell perimeter, and then I have to do some kind of detailed work to line it up. And so we did a lot of very detailed work to try to get using break lines and refinement regions to make this to align this mesh. So this next question is, hi, if I understand well, we're going to have videos about these new modules with examples for instance of scouring effects on the bridge piles. Well, let me answer the first one, and I'll let Alex kind of weigh in about scouring bridge piles or piers. Yeah. So yeah, we're trying to develop a lot of videos. There are several videos on my channel, but also that have been integrated into the user's manual. So if you go into the Non-Newtonian website user's manual, the videos are right there. And so we'll walk you through a lot of that. Sediment transport, we're starting to add those as well. We haven't done a lot of work on piers yet. And Alex, let me throw it to you about the appropriateness of 2D sediment for piers.
Yeah, I mean, you could apply 2D sediment, but I would not recommend it. Scour is such a three-dimensional process, and the resolution that you would need in 2D would be so high that I wouldn't recommend it for projects. We do have a scour calculator that's specifically designed for that, which uses empirical equations, and so that's the tool that I would recommend for that, just because it's such a high resolution 3D process.
Yeah, that's right.
It's going to be very approximate.
I agree with that. So we have the HEC 18, Federal Highway Scour tool in RAS. We also, in version 6.1, added a Riprap calculator, a Riprap sizing calculator, and some other scour tools in the hydraulic design editor. So those are there are some empirical tools in there if the process is 3D and the 2D sediment module maybe isn't appropriate.
After question? One moment.
So is the debris flow and mobile bed model available in version 6.1? Yes, it is. And it was actually available in 6.0. So the 2D sediment was beta in 6.0, and in 6.1 we took the beta tag off. So they're both in 6.1 and non-beta.
Okay. After? One moment. Okay.
Alex, you want to take this one?
Stanford, you read?
Yeah, so the question is, have you used many sediment layers and a sediment map with different grain sizes in the mobile bed model? Alex, you want to take that, or you want me to?
Yes, that's a very common thing to do. For most field applications, you do that.
So for example, here in the model we're showing right now, we use the land use to each of these land use colors has a bed gradation associated with it. But then Alex has added this stratigraphic model, so your initial conditions can have different layers as well.
Yeah, the most common use for the bed layers is when you have a non-erodible surface. And so you would specify a couple of bed layers on top and then one layer that's actually a non-erodible surface underneath.
Okay.
So Marco asks, providing that not all rainy events are able to trigger debris flow, can HEC RAS software foresee which ones can trigger debris and in a slope? So that's not going to be RAS. RAS basically assumes that you have to give RAS the concentration. So RAS assumes the concentration coming in. But 𝗔𝗟𝗃, Dr. 𝗔𝗃 here at HEC has added, at the same time that we've been adding mud and debris flow to RAS, he has been adding mud and debris wash-off tools to our sediment yield equations to HEC HMS. And so he has 5 or 6 mud and debris yield equations in HEC HMS, and they have thresholds. And so when I went back and I showed you, this, where I said, this was our Santa Barbara model without calibrating. What we did is we used HMS and those they're post-wildfire sediment yield equations to determine what the sediment yield would be. And so we used HMS to figure out the concentration coming in, and then used RAS to route it. And so HMS is developing side by side with RAS, and is also going to be able to provide you some of this information.
Next question.
So I'm assuming that, so the question is, do you have any recommended ranges of values for certain materials? And I assume that you're talking about the mud and debris parameters, because those are difficult to come up with. We have included information from Julian's textbook. Professor Julian at Colorado State has a textbook on this, and we just have reproduced the information from his textbook and have there are exponential equations that are pretty common, where you have essentially the viscosity and the yield strength are exponential functions of the volumetric concentration. And then we provide the coefficients that Julian lays out for different materials. And so again, back to this here, what did we do? We used those exponential equations out of Julian's that were in O'Brien's material. Jim O'Brien did a bunch of work on non-Newtonian with Julian. And so we used those equations with the default parameters for what they call normal soil. And so that's how we got this uncalibrated result, is we used the HMS yield equations to tell us how much sediment was delivered. And then we used Julian's equations with parameters for normal soil to determine our non-Newtonian parameters, and this was the result. Those are all in the user's manual. And so I'd recommend the user's documentation for this is pretty good. But the other thing is that now that this is in RAS, a lot more people are going to do it. And so I think that we're going to start to compile a lot more information about what these parameters should be.
Okay. Next.
So the question, Alex, I'm going to let you talk about this. The question is, which is the size of the models? Are there any practical limits to the choice of mesh size?
Yeah, that really depends on the scale of the model. So the size of your grid cell sizes, because if you have large cells and you can use bigger time steps, you can get away with longer simulations, use bigger meshes. But in terms of like just the mesh size, it's going to depend on whether you're doing just hydraulics and just hydraulics with non-Newtonian flow, or if you're adding sediment. Sediment requires a lot more memory than hydraulics, 2 orders of magnitude more, because of all of the bed layers and grain classes. And when you're using sediment, it's going to be a lot slower too, because we solve transport equations for each grain class, and we solve the bed sorting and layering equations. So sediment is more computationally intensive than flow. Non-Newtonian flow by itself is just a little bit more computationally intensive than Newtonian flow, but not very much. We've done hydraulic models that are about 1 million cells in size. But for sediment models, I think 80,000 cells, 100,000 cells is probably your upper limit, and that would be kind of pushing it. most practical models are like 30 to 60,000 cells.
The Chippewa model that I showed you, I forget how many cells are in it, but it covers a few miles. Running a couple of months, you have to do it overnight. It's going to be 10 hours to run a couple of months in a domain that size.
Okay.
So is it possible to retrieve debris mobilized volume and velocity outputs triggered by a rainy event following an HEC RAS simulation? Where can I find these values in HEC RAS? So there's good news and there's bad news here. This is a manuscript that we're submitting today. So you all are getting a preview of this manuscript that we're submitting on the Brumahilo and the Santa Barbara models. We're submitting this to Geosciences, and what we've got here is it's a standard velocity output from HEC RAS of these debris flows. We also write the non-Newtonian parameters to the HDF files, but you can get all the standard velocity outputs from RAS from the non-Newtonian and actually get some of the non-Newtonian parameters. Volume is another issue. One of the things that we've noticed in sediment transport, for example, if you look at the Chippewa result, one of the things that we're going to want on the Chippewa result is, we have these depths in the cells, but what we're comparing it to is actual dredge volumes. And so we actually have to accumulate this bed change into a total volume. And we don't have tools to do that in RAS right now. We're adding them. We're hoping that they're going to be in 6.3. So what do you do if you want that? Well, we write all of our results to a tool a storage file called HDF5. HDF5 was developed by NASA. It's a very compressible, very quick binary file. All of the RAS output is going to that. And R, Python, and MATLAB all have great libraries to interact with HDF5. And so I just wrote a little script that went and pulled all these depths and integrated them. And if you look at, if we go back to this Flume study, this velocity distribution, this lateral velocity distribution, that's not actually something that you can get from RAS yet. We're working on the RAS mapper output, but all I did is I wrote an R script that went and pulled these velocities from these faces. And in this paper, I actually included the R script in the paper. If you go to the sediment transport manual in RAS and just write R or Python, it'll take you to some R, MATLAB, and Python scripts that people use to interact with the results that they want. And then just tell us what's on your list, and we'll do our best to keep adding it to Mapper.
We have 2 questions about Roberto first.
What are the main differences between HEC RAS and Flow 2D? Alex, do you want to take this, or you want me to do it?
Well, the main difference that comes to mind is the subgrid capabilities. There's a lot of details about the governing equations are different, the numerical methods are different. We both have non-Newtonian flow. I mean, the capabilities there's just a lot of differences. It depends on what kind of project and application that you want to do, which one I would choose. I think RAS is going to be better. Obviously, I'm biased. For most applications, I think RAS is going to be the better model, but yeah.
Okay. Second and third. Stan.
Oh, we lost Stan. I can. All right.
You show a question?
I got dropped. I ended up.
Okay.
You can keep going if you want.
For steep channels, that lab data set that Stan showed, the USGS Flume experiment, it's almost prototype scale, had a slope of 31 degrees. That's really pushing it for RAS. The non-Newtonian flow, because it's designed for, or it's usually used for steep terrain, we added slope corrections in the governing equations and the momentum equations. And because of that, it's able to handle steeper slopes better than regular RAS, Newtonian flow. That's something that we're going to do in the future. We're going to add those slope corrections to the Newtonian flow model. But there's been studies, UC Davis here, our local university did a study where they applied RAS for different slopes and look at the accuracy. And they suggested slopes of about 11% were good with HEC RAS. And then even 15, they started to see problems in the solution. So that's about how steep I would apply HEC RAS, 11 to 15% slopes.
Okay. Last question about Roberto.
The new equations resolution inserted in 6.1 seems to be more reliable. Alex, do you know which equations they're talking about?
No, new equations.
Roberto, quale equazione?
So we fixed some bugs in 6.1. So I'd like to think that each version is more reliable than the last.
Yes.
I guess is what I would say. We did release the non-Newtonian example data set that we released with 6.0 actually stopped working. And so you can go and download that again. Yeah, it is slightly more reliable. We fixed a couple bugs, but they're generally the same equations.
Okay. Wait, you did this question.
Oh.
Wait, one moment.
We're solving the same equations.
Okay. Wait.
Oh, looks like we lost Antonio. So let me Mubashar has a question asking, can RAS2D be used to estimate sediment erosion and deposition in torrents? Alex, do you have thoughts on that? Or you want me to take that?
Yeah, I don't see the question.
Right there. Can RAS2D be used to estimate sediment erosion and deposition in torrents?
Yeah, I think so.
And I think that especially now that you can connect both non-Newtonian and sediment transport,
Yeah.
the main limitation I think in those settings is head cuts, right? Where it's not a head cut model, it's a transport model.
That's right.
So Marco asks if we have an example of an HDF, Python, or MATLAB file. Oh, okay, sorry. Do you have recommended values for certain materials in tailing ponds? We are still kind of getting into that world. We're, as far as the parameterization of these, that's not our specialty. There is a substantial literature on that that we've cited in our paper, but we ended up using for the Brumahilo, we ended up using parameters that were developed for us.
Okay.
I guess again, as this happens, as these models happen more, I think that we'll develop a better sense for that. But the paper that we're submitting today has a pretty good lit review on sources of that information. So that hopefully that'll come out soon. And then Marco, so Alex uses MATLAB, I use R. Neither of us use Python very much, but we've seen all three. In the manual, if you search the RAS manual online for Python, I think that there is some sample data in there, not that I didn't write, but there are papers with sample data for sample code for interacting with the HDF5 files. There's Tomas is a academic from Poland who he's published information about interacting with the HDF5 file in the HDF5 file using Python. That would be your best bet. And if you guys develop code for interacting with the HDF5 file, then I have a place there where I just am going to start including sample code, so that people can kind of do whatever they want with the HDF5 file. It's actually not that hard, but yeah, you can also download HDFView. It's a free HDF5 viewer, and you can copy and paste into Excel. That's a little painful if you have to do it a lot, but it's a HDFView will give you access to all of the results in HDF5. All right, I can't tell if I've been dropped or if we've lost Alex and Antonio, but I don't see any more questions. But I guess, oh, here we go. Yeah, no problem, Marco. I guess I'll hang around for a couple of minutes. If anyone has any other questions, I'll plan to leave at 10:30. How about that? 10:30 my time. I guess that's 7:30 your time.
Okay.
You guys are back. You're back.
Okay. Okay. Thank you all. And the next webinar. And Merry Christmas. Ciao.
You too, Antonio.
Thank
Bye.
you. Bye-bye, everyone.
Ciao. No.